Thank you for joining. This is our 60th session on Timescale for Finance, and I'm very happy that we are concluding this small set of presentations. And today we are going to talk about compression and retention and how to save storage in general. So that's our session, and especially a reminder that we are doing this as a community and as a way that we can also aggregate knowledge from folks that are on the finance sector. And and the idea is that it can speed up the adoption of new timescale technology on new things. And from the perspective of what we have here, this this is all in the /templates. And today we are going to go deep into the algorithms and why the things works as they work. So this is more like a comprehension of both things. So just a reminder of where we are here. We are talking about marked data stream, and we are storing ticks. So it's like a trade data. So we have a time, symbol, price, and volume. And this is our hyper table that is also being partitioned by 1 day. So this is partition is also compressed by 1 week. And then we also have a compression policy that will just do it in background. And then we have hierarchical continuous aggregates to just generate candlesticks on top of every data that is in the database. And let's start with the topic of today. So both retention and compression are background jobs, and they are policies. So we can just stable these policies. Policies are metadata that we say, well, we want to have this routine running every X hours or every X days, and then it will try to achieve a task doing some specific job, like compress a chunk or even drop a chunk. So in the compression, we are going to compress. In the retention, we may drop the chunk. We are going to be going much more deep today in compression, but we are also going to cover a bit of retention and the most insightful parts of like why retention is important and how it can help to speed up your database. So compression and retention, this is only 2 lines of code, but it can mess up everything if it's misconfigured. And depending on how you configure, you say, wow, compression is not working. I put it and I don't have any effects, or retention can mess up with everything because you can just lost your data. So be very careful with how you use these lines, and also learn how to get the best of this both cases. So let's start with compression. So this is a very insane down amount of storage after compression. So you can see here, this is a real case from community. Just someone installed the extension, make it compress everything, and then they jumped from 34 terabytes to 2.3 terabytes. So in general, we see community reporting something around 95% compression. And if you're not getting there, maybe your business domain or something will not allow you to get so high level of compression, but you can also figure out ways to overcome and strategy the way that you organize your data to get better compression. So that's why we are here today, to just understand the underlying algorithms that will go over your data. So if we are talking about 95% compression ratio, it means that we are only using 5% of the storage. So it means that you can put 20 times more data. And this is the simplest template setup, that you add compression and then you get this type of savings already on the go. So this is a compression based in the time dimension. So as your data gets older, probably you are not going to read it too much, and you you're also not going to update it very often. So you can just compress it and let it be archived, right? So that's the idea but compression has several benefits, and for having a good compression, you should not ignore the optional arguments. So they are optionals, they have some defaults, but it's very good that you configure them because they will speed up the way you can query on compressed data. So especially the segment by will make the right cluster of your data. So let's say, for example, you have a generic table, like a narrow table, which you have metrics from several, let's say, for example, we are talking about market data. We can say if we have a table and we forget to compress and segment by the symbol, we are going to not be able to get good deltas between the prices because you not be able to apply the right algorithms. And the same for the order by, because sometimes you want to search for something that you are searching for some price range, or you are searching for specific types of things that if your data is already organized when you are compressing the data, you don't need to have indices. You just use the compressed data in the right order, and then you already have everything that you need. And recently, we have this experimental compressed chunk time interval. And it's very cool because you can merge multiple 1 minute, let's say, for example, if you want to compress chunks one day in 1 week, you can compress them all. And when you decompress, they will get back to their original shape of one day. So that's very cool. And compress is interesting because first thing is that it compresses the entire partition. So let's say when you are doing a lock, you are locking a record of row by row, or you are locking something. In this case, what we are locking is the entire, let's say, hypertable reference. So we make a process that compresses a chunk, and then when we have the entire other chunk entire compressed, we just swap the chunk reference into the metadata level. And that's how we do it. And then we discard the old one, like we truncate the table, right? And this is less indices and less and more segments. So as you start mapping how your data should be organized, you start like building these small boxes that they will be queried in the right way. As you have columnar storage and you can compress them down, it's a very important thing that you understand how this works. So let's jump into the algorithms. So for integers, timestamps, most of the common uses are delta encoding, delta of delta, simple 8 bits, and run length encoding. For columns that have a high amount, they will use different short-based compression and some dictionary as well. Dictionary is very interesting because dictionary is the most efficient one. You just convert everything to a text and start observing the patterns, and then you can just make these patterns as small reference and builds a map, and then it really shrinks down the data if you have repeated patterns. So this is an example. I couldn't have the time to translate this example. I just copied from our official docs to a financial example. But the idea here is that we are having a table with temperature and humidity, some CPU, some 4 different metrics in the same table. And then if we are going to compress it, what we can do is we can apply some small deltas between temperatures, for example, and also between the memory and the CPU and so on. So instead of having like bigger numbers, we start having smaller numbers. And then we can also understand that we can have the delta of the delta and just like work from the previous to the next, and then it will be even smaller numbers. that's how these small algorithms just like simplify the numbers that you have and the text and the data. And in the 8-bit, you have this type of, let's say, repeated values that are like a pattern, right? So take some time to read the sequence of temperatures and take a look in how it represents. So for all these types of repeated values, you can see that this is very interesting. So you can imagine it on trading volumes, like generally you have like 100, 100, 200, and then you have like very compatible numbers, and sometimes they are like exactly the same unit for quite long and for long sequence. So this is a very welcome algorithms in these circumstances. And you can also think about dictionary. So dictionary is just like a hash map for referencing values, and then you can just start building these marks in the middle of your text that you can expand to the dictionary, right? So we also have the gorilla compression for floating point numbers, and this is a very interesting one. You can imagine like floating numbers. Sometimes they you can simplify them, and then you can apply different algorithms like the previous one. So this is a mix of algorithms that works, and they are very, very flexible. So and ultimately, talking about being flexible, we explored going further into how we organize internally our compression. So we call it now mutable compression. And so here you can see how the data looks like flat versus the data compressed. So you have data nested into arrays. So you can have like a columnar storage that you say, well, from this last hour, I have 5 records. Here are all the temperatures. Here are all the devices, and so on. So, and then you have these arrays, and you can compress the arrays. And these batches comes in like 1,000 per segment. So let's say if you're talking about device ID 1, then you have all the temperatures of the device ID 1, all the time, and so on. And then you can see that it applies different algorithms. But now let's think about a new tuple that arrives. Let's say I have a backfill that just comes. I need to insert data that arrived, and this is in the middle of a compressed chunk, right? So in this case, we have this new, let's say, single line compressed into a separated space. We call it staging area. So in this staging area, we just say, well, we have this new chunk. We are going to put it there. Whatever kind of query we do, we are going to also consider anything that's in the staging area, and we are going to mark this chunk to be recompressed so we can merge this information later. So that's how it works. It goes and combine both cases, and then it builds your query considering this staging area. Later, when you decompress, it will just be part of the data, and when you compress back, it will just disappear. So if you think about how it works in this case, for example, if you send one update request, you have more things in the staging area, and then you'll be combining more things in the staging area. But when you mark it to recompress, then you move it back to the original state, and then the staging area is empty. So that's how it works internally. So whenever you make changes, that's the way it acts, and that's how it goes and check and make this change. So this is a good design to think. So like you have just a background worker that checks what needs to be recompressed, and it's much more simpler to just say, well, we have a dirty chunk here. Let's put this data aside. Let's combine this data, and then when we recompress, we make it compress with high ratios again. So and the recompressing is also part of the background job. So it can also make it work with 20x more data. So talking about 20x more data, let's talk about 20x less data. So let's think about retention. So retention is interesting because you can control your data size. Just think that when you add the retention, you just establish the limit of your database. So let's do some math here. So let's imagine a scenario that we are talking about ticks, and we are putting a 6-month retention policy for the ticks, right? And let's say we are receiving data 1 billion rows per day, around 100K instruments. So it means that we would have 108 billion rows every 6 months, okay? So knowing this is a final number. We know that from this perspective, we have a static growth. So we have always 108 billion rows of raw data plus something else that is like candlesticks. So for example, let's say if I have 1 day retention, I would just hold 1 billion rows, and then that's all my, like the most of my data set, and the rest of my data set will grow in a static rate, and I can measure this static rate. So let's imagine this example. 1 day with 1 billion rows, let's say if I'm getting 1 minute candlesticks of 100K instruments or symbols, how you want to say it. Instruments here means like the stock or something like that. So I would have like 360 million candlesticks, rows of candlesticks, right? So what it means is that I have this, let's say 1.6, 1.4 billion rows per day. So I have 1 billion rows of raw data plus 360 million rows of candlesticks and 1.4 billion row per day. So I can consider, like, for example, this 362 million rows per day is a static growth, right? And that's my growth. That's how I define my minimal frame. So maybe I can just think like, oh no, maybe I can do 30 seconds and have 700 million rows of candlesticks, and then I have a higher resolution of my data, but still drag and be able to project the size of my data. And that's the most important lesson of using retention. So you always can use it in your favor. And let's talk about how it works. This is so cool because this is one of the ways that also make Timescale very magical. So this is a truncate method. So if you're not familiar, you can just say truncate and the table name, and it's like you say delete from your table name without the word clause, but it just swipes the entire file reference. So it's like echo/dev/new into your file pointer. So it will just erase the file. And why it's so good? Because you are going to erase all the statistics. All statistics goes into chunks, and then you don't need to update statistics. If you do, for example, a delete with the where clause, which you are going to say, where my time range is between this and that month, then you are going to do row by row, mark them as deleted, and then you need to go and clean this memory, reuse this disk space, rework in this, and also update our Postgres statistics to make query plans faster. So in this way, query plans will just be very, very fair without needing to vacuum or anything like this. And our indices are also truncated together because they are there already. So removing the whole chunk is a very good idea. And that's our last session, folks. So that's about compression and side effects. That was great. I hope you enjoy it as I enjoy it. And if anyone would like to be participating, Nelson will be bringing us something on May 10th. I will be shooting the the invites when we have it. And he will show his fintech case. It's a very cool case, 𝗥𝗲𝗹𝗲𝘃. You can check this out. And I would love to have more, let's say, community sessions driven by community members. So JS was asking, hey, anyone who knows a way to create like Renko handles inside TimescaleDB? And I was like, let's make a session and build it, because Postgres is so flexible that it's easy. We can hack this code together. So if anyone is up for sessions, just come to the community and say, hey, I'd love to lead this session. I'd love to participate on this. And I can offer to organize the logistics and also put the calendar invites and share it later with everybody. So that's all for today. Thank you very much. And I hope you enjoy it, and see you soon in the next 2 weeks.